so related rates. Related rates are sort of as they sound. We're going to solve problems that involve several rates that are related to one another. So for example, if you can imagine, have you guys ever had like a flat basketball or something and you pump air into it with an air pump? Yeah, you can imagine that? Okay, so when you think about time, the volume of the ball is changing relative to time, okay? The radius of the ball is also changing relative to time, okay? Those two rates are different to one another, but they are also related to one another because the radius of the ball is related to the volume of the ball. So we're not necessarily going to be looking at the rate of the radius with respect to volume. We're going to be looking at the rate of volume with respect to time and radius with respect to time, and looking at both of those to solve one problem. So that's sort of the way that the rates are not the same thing, but they are very much related to one another because of the fact that radius is related to the volume of a sphere. Does that kind of make sense? Okay, so I think that's probably the best way of prefacing this thing, but it's probably easiest to just jump into a problem. And in fact, I think the problem that we're about to jump into is the one that I just spoke about. Okay, and just like with the max-min problems, these problems can seem a little bit daunting at first if you've never seen them before. But once you see 5, 10 of them, you'll notice that they do get quite repetitive and that you'll start to get a feel of what to do, okay? And I'm gonna give you as much of a step-by-step process as I can, okay? So let's read through this one first. All right, air is pumped into a spherical balloon so its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so when the diameter is specifically 50 centimeters, how fast is the radius increasing at that instant in time? Okay, all right, so here's what we're going to do. We're going to start out, always, if you can, by drawing a diagram. Just get a sense of what you're dealing with. Okay, so we've got a sphere. And we're looking at the volume of a sphere and the radius of a sphere. And so we should probably write down the formula for the volume of a sphere, which is 4 over 3 pi r cubed. That's on your formula sheet, if you don't remember what it is. And sometimes the diagrams will be much more involved than this one is. Okay, but that's really all that we can do for now. Okay, now notice we're not looking here at how is the volume changing with respect to the radius. If that was the case, we just have to differentiate volume with respect to r, right? That's something that we've sort of already looked at. Okay, we're looking at how is the radius changing with respect to time? Time isn't actually in this equation yet. Okay, so the second thing that we're going to do is we're going to sort of write out what we know and write out explicitly what we are being asked to find. Okay, so here's what we know. We know that the change in volume with respect to time is 100 centimeters cubed per second. So that is, actually I should write out the second step. What do we know? And what do we want to find out? Okay, so one thing we know is this. Volume increases at a rate of 100 centimeters cubed per second. Per second means with respect to time. Okay, so that is dV by dt. Okay, instantaneous change in volume with respect to time. And that is 100. We know that. Whoops. What we want to know is how fast is the radius increasing with respect to time when the diameter is 50? That's what we want to know. Okay. Well, diameter equals 50. I mean, the diameter isn't exactly in this equation, but if the diameter is 50, then what do we know? Radius is 25. Okay? So you can sort of say I.e. r equals 25. Okay? So here's what we're going to do. We've got this equation connecting volume and radius. We are going to differentiate this with respect to time. We're not going to take dV by dr. We're going to, this is like implicit differentiation, differentiate both sides with respect to time. Okay, so this is sort of step 3. Actually, maybe I'll just write it on a separate line. Okay, now we already have this equation, but sometimes you'll have to sort of come up with it. Find a way to connect the variables that are related and then differentiate both of them with respect to time. Okay, we have that already. So in step 3, we're going to take this and differentiate both sides with respect to time. Okay, so here's what it's going to look like. d by dt of volume equals d by dt of 4/3 pi r squared. Cubed. That's important. Okay. Now, this side on the left is just dV by dt. Okay, because if you can imagine with implicit differentiation, the derivative of v is just 1. Right? So it's kind of like 1 times dV by dt, which is just dV by dt. The right side, if we're doing implicit differentiation here, then we'd have to take the derivative of this and then multiply it by dr by dt. Okay, so that is going to give us, if we take the derivative of this piece, 3 times 4/3 pi r squared. Actually, I don't know why I put that in brackets. Okay, and then times dr by dt. And the reason why we have to multiply it by dr by dt is, again, because we're not differentiating like the left side with respect to r. We're differentiating both sides with respect to t. Okay, and then this becomes, these cancel. So we're going to get dv by dt equals 4 pi r squared times dr by dt. Okay, now at this stage, we know everything except for one unknown. We know dv by dt, that's 100. What we're looking for is what is dr by dt when r is 25. So right now, what we can do is sub in what you know, to solve for dr by dt. Okay, and remember, we're only solving for dr by dt when the radius is 25 centimeters. As soon as the radius changes, then that rate is also going to change. But at that moment in time, we can solve for dr by dt, the rate that the radius is changing by. Okay, so we're going to sub in what we know. We know that this, dv by dt, is 100. We know that r is 25. Whoops. Okay, so that is going to give us 25 times 4 is 100, so that's 400. 100 equals, no, because we took the derivative, right? So when we took the derivative, then this became squared. The 3 came in front, and this became squared. Yeah? Okay. I'm doing too much in my head. What's 25 squared is 625 times 4, 2,500. 2,500 pi times dr by dt. I think. Someone confirm that. Well, 4 times 25 is 100, times 25 again should be 2,500. There we go. I think that's right. Okay, so then we just divide by 2,500 pi. And we're going to get that dr by dt is 1 over 25 pi. Or, I mean, if you, like, realistically, you'd probably actually want to know what the decimal approximation of the value of the rate of change is here. So that is what? That's about 0.013 centimeters per second, approximately. Okay, so you could say now that when the diameter is 50 centimeters, the radius is increasing by 0.013 centimeters per second. It's essentially what we're finding there. All right. Any questions? Are you guys ready to move on to the next one? No? Okay. Cool. Let's try another one. Okay, so a ladder 10 feet tall rests against a vertical wall. If the bottom slides away from the wall at a rate of 1 foot per second, how fast is the top sliding down when the bottom of the ladder is 6 feet from the wall? Okay, so we are going to start by drawing a picture. Okay, so we've got, here's a wall, here's the floor, here's the ladder. And this is a very nice right angle between the floor and the wall. That's important. And what we know is that the ladder is 10 feet long. So this is 10 feet. Okay? And let's say that we call this horizontal distance x and this vertical distance y. Okay, so that's a pretty nice diagram right now. Okay, do we have any sort of, can we come up with any sort of equations that relate any of these variables together at this point? Pythagoras, exactly. So let's write that down. We know that x squared plus y squared equals 10 squared. Okay? Now, what do we know and what do we want to know? Okay? Well, if the bottom slides away from the wall, so essentially this is going to kind of move this way. If you can imagine it sliding down, probably not a good situation if you're standing on it. Then as this slides down, this top is going to also slide down. As this slides sort of towards the right, or my right, as opposed, yeah, it's your right as well, because I'm facing the board, then the top of the ladder is going to slide down towards the ground. Okay? So what we want to know is, in step 2, we know that the change in the horizontal, that's the change in x with respect to time. Okay, is 1. Okay, if the bottom slides away at a rate of 1 foot per second, what we want to know is what is the change in the vertical when the bottom of the ladder, when x is 6. That's what we want to know, essentially. Okay. Now, we could start to go into step 3 right now, which is take this equation, this Pythagorean theorem, and differentiate everything with respect to time. And I think I'd like to do that because my guess is that that's what most of you guys will do. Okay, and then what we're going to do is we're going to backtrack because we're going to find out that we're going to have a problem. We're going to have too many variables. Okay, so let's see what happens. We're going to have to actually add to step 2. But what I'd like to do is sort of model the process that I think most students would go through so that you can see that if you get stuck, oh, actually we could go back and see what else we can fill in step 2 to try and make this work. Okay? So let's say we now differentiate. Okay, so we're going to go d by dt of x squared plus d by dt of y squared equals d by dt of 10. Okay? And when we differentiate the first term on the left, we will get 2x times dx by dt. And then for the second term, we're going to get 2y times dy by dt. And then on the right, we're going to get 0. Okay. Now, if we tried at this stage to fill in what we know, which is what we did in the last problem, what's going to happen? We have too many unknowns, exactly. Because we know what x is, we know what dx by dt is, but we don't know what y is, and we're looking for dy by dt. So we have to try and figure out what y is. Okay. Now, when x is 6, the picture looks like this. Do we have enough information to figure out y when x is 6? Yes, exactly. So we've got to take that extra step and figure out, at the time that x is 6, what is y? Okay? So y is going to be basically the square root of 10 squared minus 6 squared, which is 100 minus 36 is 64, so y is 8. And now we have enough information to plug in what we know and solve for what we don't know. Okay, so we know that x is 6, so we're going to go 2 times 6. Dx by dt is 1 times 1 plus 2 times y is 8 times dy by dt, we don't know, equals 0. Okay, and we're going to get 12 plus 16 dy by dt equals 0. And so we can now solve for dy by dt. Right, we'll get 16 dy by dt equals negative 12. Divide by 16, dy by dt, whoops, y by dt equals negative 12 over 16, which is negative 3 over 4, which is also negative 0.75 feet per second. Is it per second or per minute? Per second. There we go. Exactly. It's negative because it's sliding down. Precisely. Yep. Okay, so we can now say that, what does the question ask? When the ladder is 6 feet from the wall, or I should say when the bottom of the ladder is 6 feet from the wall. the ladder is sliding down the wall. At a rate of 0.75 feet per second, right? And because I, in my description, have said it's sliding down, I can just use the magnitude 0.75, right? And in fact, it would be incorrect to say it's sliding down at a rate of negative 0.75, because then you're almost putting in double negatives. All right. Any questions with this one? No? Okay. So I think we'll do one more today, and then we'll come back to this on Thursday. Let me see which one I want to do. What's that?
Tomorrow's review, right?
Yes.
And then the Unit 3 assignment is due on Wednesday.
Yes. Yeah, let's do this one. Okay. Okay, so a water tank has the shape of an inverted cone with a base radius of 2 meters and a height of 4 meters. If water is pumped in at a rate of 2 meters cubed per minute, find the rate the water level is rising when the water is 3 meters deep. Okay, so we are going to start by drawing a diagram. Yeah, it's a weird water tank, you're right. Maybe you have like a lot of storage that you collect at the bottom of your floor and then you have space at the top, so you have this cone shape. I don't know. Who knows? Yeah, it's like a funnel. So here's your water tank. Okay, and let's see. The base radius is 2 meters. And the height is 4. Okay, and do you guys know volume of a cone? No, that's on your formula sheet as well. But in general, a cone is sort of follows the same rules as pyramids. And pyramids are always 1/3 the volume of their corresponding prism. So the prism, the quote-unquote prism, would be the cylinder, right, which is pi r squared h. So the volume for this is 1/3 pi r squared h. Yes?
Why is it not like upside down? Because it says inverted cone.
It says it is inverted. Oh, well, I suppose if you think it's a tank, you'd think that the base of it would be on the bottom, I suppose. I don't know. I suppose it depends on which way you think a cone should go, right? If it's like an ice cream cone, then this isn't inverted. But if it's a traffic cone, then this is inverted. It should just say cone. There, cone. I don't know. Cone. Doesn't matter. We're just looking at the volume of this thing. Volume doesn't change with the orientation. Okay. So there is the diagram. Okay? Now we want to know, what do we know? What do we know? So this is step 1. What do we know? What do we know? We know that the rate that the volume is being pumped, so that's the change in volume, right? If it's being pumped in, then the volume is changing at this rate. So that's dV by dt equals 2 meters cubed per minute. Okay, now there's actually something else that we know here that isn't explicitly given to us, but that we should be able to pick up from in the diagram. And that is that there's a relationship between the height and the radius. Can you guys see what it is? the height of the cone and the radius of the cone. And it's going to be true no matter what the water level, because you're going to have similar triangles, right? So if I had the water level over here, right, we have like a similar triangle here. So these are still going to be proportional to one another, right? The ratio of the radius to the height, for example, will be proportional no matter what the water level is. What is the relationship between the radius and the height? Yeah. Yeah, the radius is half the height, exactly. So that's going to become important, and it's important because right now we've got 3 variables in this equation that relates volume to radius and height. And what we want to know is we've got the change in volume with respect to time. We want to know the change in height with respect to time. Okay, so we've got too many variables right now. So that connection between the height and the radius is quite an important one, right? So 2 times the radius equals the height. We know that as well. Okay, and what we want to know, or in fact, what we're going to want to replace in this equation, because we want to know the change in height with respect to time, is we're going to want to replace the radius, right? So we know that radius is the height divided by 2. Okay, so we are going to take this, sub it in there in a minute. Okay, but what we want to know is what is dH by dt when h is 3? That's what we're looking for. Okay, so let's do this substitution first, and then we can go and differentiate both sides with respect to t. So if I substitute in, I'm going to get volume equals 1/3 pi times h over 2 squared times h. Okay, and if I simplify that a little bit, that will be 1/3 pi times h squared over 4 times h. And all together, I have a denominator 3 here, a denominator of 4 here. That is over 12, right? And then in the numerator, I've got pi h cubed. Okay, so now I've got volume only related to h for this specific cone, right? Because of course in other cones, you're not going to have that same relationship where the height is exactly twice the radius. Okay, and now we can differentiate both sides with respect to t, to time. So this is step 3. Okay, so we're going to have d by dt of v equals d by dt of pi over 12 h cubed and on the left we just have dv by dt, and on the right we will have 3 times pi h squared over 12 times dh by dt. Or this can be simplified, I suppose, to dv by dt equals pi h squared over 4 times dv by dt. Or no, dh, I'm sorry. dh by dt okay? And then at this stage, you can sub in what you know. Some people actually like to solve for dH by dt first and then sub in at the end. That's sort of the physics style of doing things. You can certainly do that too, okay? That's fine. Either way. Okay, so now sub in what you know. And at this stage, we know dv by dt is 2 pi. And then h was 3, right? You think? We wanted to know the change in height with respect to time when the height was 3. So pi times 3 squared over 4 times dh by dt. So that is going to be multiplied by 4. So 8 equals 9 pi times dh by dt. Which means that dH by dt equals 8 over 9 pi, or what is that in, I don't know. .28 meters per minute. Okay, the change in volume was in meters cubed per minute. The change in height is going to be in meters per minute. Okay, so we could say that when the height is at 3 meters, the height is changing at a rate of 0.28 rather, meters per minute. Our height is increasing, I could say, at a rate of 0.28 meters per minute. Yeah.
Why did you get 0.28?
Is that not what it was?
No, my calculator says 2.8. So like, why do you add?
Okay, did you put, when you went 8 divided by 9 pi, did you put the 9 pi in brackets in the denominator?
No.
That's why, yeah. Yeah, because otherwise it'll go 8 divided by 9 and then multiply it by pi.
Oh,
Yeah.
yeah.
Yeah. That's why it's good to like put both down, so that if you make that mistake, then I'll just give you full marks for having that. Yeah. Yeah. Okay, I'll come look in a sec, okay? All right, so I'm going to leave it there for today.